This video is on Quincy's predictive coding capability. We're going to explore a few sort of subtopics there. What is it? What is predictive coding in general? How is it different than what summation has? And how do you interpret the results? So first, just in general, let's talk about what it is. Predictive coding is meant to take some set of documents that you have already coded and generate the most efficient Boolean search that will separate your documents into responsive and non-responsive documents. So you take a set of documents you've coded as responsive and a set of documents you've coded as not responsive. And it, with the fewest possible keywords, will attempt to separate all those documents into those two groups, responsive and not responsive. So if you go through, let's say, and code 1,000 documents as responsive because they have the word Bob in them, and another 1,000 documents as non-responsive because they don't have the word Bob in them, the entire predicting coding algorithm should be the word Bob, because Bob is the most efficient way to separate the two groups of documents. Obviously, you don't code on a single word, but the point is you'll code on a bunch of different concepts, a bunch of different ideas, and the algorithm will effectively go through and try to find out what's unique about the documents you said were reactive that is also not present in the documents that you said weren't reactive. And it will then take that logic and apply it to your entire data set. Now, the result of this can be you can code millions of documents really quickly, because you probably only need to code, let's say, less than 10% of the document set and then run predictive coding. But you can also get some skewed results. You can come out with predictive coding that is really not useful in terms of coding your entire document set, in terms of finding critical documents, in terms of anything like that. So we have taken a different approach in Quincy than we did in summation. We apply the same algorithm, the algorithm I just described, but we effectively unpack it for you in a nice visualization that shows you why every set of documents was coded one way or another, and you can then use those coding groups to go through and figure out if you want to accept part, all, some, none of what the predictive coding generated for you. It also puts you in a phenomenal position to explain why certain documents were coded and why they weren't. In the event that that becomes really relevant, in the event that you need to defend the coding of the documents. So I think it's very different than what other solutions you'll see on the market, because we have fully unpacked it, and I think it's quite a bit more powerful as a result of that. So let me show it to you, and then you can judge. All right. So I'm already in, I've logged into the only case I have here that's got good data on it, the predictive coding case. And I just opened up Watson and I went to the predictive coding tab. And you will always be greeted by a blank screen the first time you log in. If you've already run a predictive coding, which I have, you could just click on the build and it would pop up. But let's not do that. Let's pretend we've done nothing. So in the sort of beginning state, what you want to do is run a predictive coding job. You have to decide what label you want to call your responsive label. It can be any label you did. Any label in the entire system that you've created, you can decide is going to be your responsive category. This is another difference with summation. With summation, you have to go through and do very specific predictive coding. And so you can't really do it after the fact. It has to be almost a premeditated act. With Quincy and the Watson solution, you can do it retroactively. You can change your mind. You can flip it around. You can make the unresponsive responsive, and you can just keep running the algorithm over and over and over again on different sets until you get as much value out of it as you possibly can for a given case. Okay, we're going to do the unresponsive for this one, and then I'm just going to click run. Now it submits the job. In a second, a job thing is going to pop up, yep, showing us the job has been received and is running. It won't take very long. I'm just going to sit here and pause for a second. Okay, and when it's done, the job indicator disappears and it pops up the resulting coded tree. Now that whole process took about a minute. To save you guys time, I clipped maybe about 30 seconds out of it, but it is very quick. Well, this is a small document set. If you run a very large document set, it can actually take quite a long time. But nonetheless, in this case, it was relatively fast. And what we've got here is a tree. I coded my documents completely randomly, so it's maybe not a very intelligent tree. You're looking for a tree that is relatively even, not completely directional. But it really doesn't matter because we can unpack the algorithm and decide whether or not to keep or discard stuff. So let me start at the very beginning. Oh, by the way, you can change the orientation of the tree. If for some reason you want a horizontal tree, you can just do that. And a vertical tree, you can just do that, and you can print it. But okay, so let's go back to zooming in. We're going to zoom in. And I'm only going to look at the top part of the tree here. So first it starts off telling me the case I'm in. I'm in case 3. And how many documents total were coded. You're almost always going to have an uncoded category. Going to go down here to the uncoded. In this case, most of the documents in this case are pictures, so we can't code those. And there are 12,000 uncoded documents in this case. Total coded is the 1681. At that point, you start to get into the actual tree of the predictive coding algorithm. Each circle that isn't color coded, the clear circles, will always have a word in them. That word represented the decision point in the Boolean search. In this case, it's .m. .m, for some reason in my random coding, became actually a relatively significant term. And documents that had .m in it were all coded responsive, and documents that didn't weren't. Then you go to the next level and say, okay, well, if .m didn't exist, then Netscape became the most powerful predictive word, in which case, if it existed, those documents were not considered relevant. And if it didn't exist, you went down to team. The point is, we now know there is a certain group of 88 documents that are considered relevant only because they had the word .m in it. Now, I may be investigating something to do with .m, in which case, this is probably very much a good set of documents. But maybe I'm investigating some options fraud or something like that, and .m seems totally irrelevant to me. In that case, this might be a set of complete garbage, or maybe I want to set this aside for review more later. So how do I do that? And how do I find out what those documents are? Well, this is the secret sauce of the predictive coding in this solution. We'll zoom back in. All we need to do is click on any dot, and the grid will react. And now we can come through in our normal review fashion and look at these. And maybe we're not looking at them completely. Maybe we're not going to look at all 88 because the whole point of this was to save time. Maybe we're going to look at 10% of these and decide in general for the whole group. Or maybe we want to look at all of them together. I don't know, all of them one at a time. Depending on your case, depending on what you're doing, will help drive you to that one decision or another. Same is true, you just come down here, same is true about this one. This is a no group, there are 215. Maybe I sample these, look, these are all exactly the same document. That's an oddity of this document set. I actually had a pretty lame document set, and then I just copied it a million times to get it to this document set. So we have a lot of documents that are exactly the same. Look at one, I don't like it. discard them. Of course, in general, you would have discarded them already via deduplication, but let's pretend that's not the case. Let's pretend they're near duplicates and not complete duplicates. You could look at the group, say, hey, yes, in fact, this is total junk, and throw it away. You also don't need to go down to a specific end node. You can click on any sort of, on any node, even a non-colored one, even a clear one. And so you could come down here and say, okay, .m not exist, Netscape not exists, team exists. Maybe I actually think this whole group is relevant. Maybe I don't want to uh, make a decision off party with an I, right? So fine, I just click on that, I code this group, and I'm good to go. Anyway, I think you get the basic idea of it. The point is you can quickly unpack it. In a real case, we had a predictive coding tree that actually had 14,000 nodes. And it was in that situation really powerful in terms of allowing us to separate the documents into three groups. One is throwaway. There were a lot of nodes that had, like, say, 80,000 documents, and we would do a quick, let's say 2% sampling of the documents that were considered irrelevant, and we would just discard them. And then we had another group where it would, let's say, analogous to this .m group, or this .m group, where it said it was responsive, but we didn't really think it was responsive. The word didn't make sense to us. So we assigned those documents to a low-cost review team. And then we obviously finally had our group of documents we thought were really reactive, in this case, usually sort of towards the end of the tree. In this example, it would probably be this set of documents. I would probably go to this node because, only one document got eliminated here. It had all this other criteria to make it all the way down here. To me, that seems like, shoot, it's probably not worth discarding that document. And we would send this group off to the, highly qualified review group, if you will. And so that's how we used the algorithm. That was extremely powerful. It was extremely successful. And now you guys can, I think, do that on your own without any sort of assistance from services, because the algorithm really, like I said, unpacks it for you and gives you good sense of why stuff was done. So anyway, play around with it. I think it's super cool. I think you will find this predictive coding is more useful than any other predictive coding out there on the market. But if you have more suggestions, if you have more things you want to be able to do with this, let us know. We really want to grow this technology because we see it as a really powerful tool that we can bring to our users. So anyway, more ideas the better, but thank you very much.